Any questions from the homework? Yes, and is it Arnold?
Yeah.
Luong?
Yeah.
Okay.
Number 58, 1.4.
1.458, was that the signed one? Is that one of these ones
Yeah.
we were working on? It is a sign?
Water 60.
1.458?
I got stuck on that one.
Water 20.
1.458. So this was on the homework set, okay.
Oh. This was?
Or no, sorry.
The one after this one is on hold.
What, 58
8.
was on the homework, as in assigned to just
Yeah.
homework problems, not the
Yeah.
problem set that's being turned in. So 58, water tank has a shape obtained by revolving the curve y equals x to the 4/3 around the y-axis. And the exponent is larger than 1, it's going to have some bend in it. It's going to bend upward. If you revolve that around the y-axis, is that right?
Yeah.
Then you get this shape. Okay. So this is the curve y equals x to the 4/3. It looks kind of parabolic, not described as a parabola exactly, but very similar. Plug at the bottom is removed at 12 noon. When the depth of water in the tank is 12 feet, when the depth of the water in the tank is 12 feet. At 1, the depth of the water is 6 feet. When will the tank be empty? Okay. So some things we know is what? The, and this is Torricelli's law, which we did not talk about. Okay. So the statement of Torricelli's law is it's stated in a few different ways. Okay. So in the final form, A of y is defined to be the area of a cross section at height y. I shouldn't use x as cross section, we get it confused with x, but cross sectional area. All right. So the water, after it's been draining at some point, we can define this to be the height, y, yeah. Okay. At time t. All right, so A of y represents the area of a cross section. And t is just time. And what do they give us? Hours, probably. Okay. They tell us initial height, right? Depth of the water tank is 12 feet when they pull the plug. At 1 p.m., the depth of the water is 6 feet. So we could use hours, I suppose, for time. And what does Torricelli's law say? dy dt. So there's a few different versions. There's one of them that involves the volume, the rate of change of the volume of the liquid in the container with respect to time. And then the other one talks about the height, okay? After doing some calculus and relating the volume and the height, right? So it requires the cross-sectional area. That's why they do that integral in general. But the form that we could use, A of y dy dt equals negative k times square root y, where y represents the height at time t, k is a constant which we will have to find, and that gives us the height at the area of a cross-sectional slice with height of y. So can we find that?
Yeah.
Yeah. So if the height is, if we're given a height y, can we find the radius at least of the liquid?
Oh, it's actually going to be
So this is as a function, the y is a function, if I know y, then I want to find the area as a function of y. But one thing we can do is find the radius. Now this curve gives us the height y in terms of x, but if we turn that around, given y, this x value would be the radius of that cross-sectional slice. Okay? So invert this, and the radius at any height y would be what?
3/4.
Yeah, raise both sides to the 3/4. Okay, so that would be the radius. So what would the area of a cross-sectional slice be?
Y to the 6/4. Yeah, 6/4 times pi.
Pi times the radius, I'm doing it sub y, the radius in terms of y, r sub y squared. So this would be pi times, taking it slow, y to the 3/4 squared, but if I square that, that's where you got the 6/8? Is it 6/8 or is it 6/4?
6/4 is what I said.
6/4.
but I don't know
Okay,
that
right.
actually.
Okay, you're right. Because we're multiplying, power raised to a power, that gives us 6/4 or 3/2. So that would be the area of a cross-sectional slice. Okay, so this law would become, I can just divide both sides by y, a of y, right? Another way of writing it, dy dt equals negative k root y over a of y, okay, which is this. So now we're going to use more exponent properties, y to the 1/2, and a of y, pi, y to the 3/2. And then how do I handle these powers of y in the numerator denominator? Subtracting, right, subtract. Starting from here, subtract the power in the denominator. 1/2 minus 3/2 is negative 2/2, negative 1. Oops, k over pi. Y to the negative 1 we can write. Now, is this separable? dy dt. And of course, we know that y itself is a function of time. Over time, the height is decreasing because there's a little plug that's going to be opened up at the bottom where water is going to be draining out. So y is a function of t. R is a function of y. Okay. So we got all this business, or we could write it as negative k. Negative k over pi y. And if I want to, is this separable? I hope so. It's in section 1.4. All right, so section 1.4, this is separable. Now, there's my function of y is 1 over y. So if I imagine multiplying both sides by y and both sides by dt, we can separate the variables on either side of the equation with their appropriate differentials. So I could leave the negative with that business. So I could call this negative y, or sorry, y dy equals negative k over pi dt. All right, we on the right track?
So,
I hope so. We're going somewhere. We're going somewhere with it. All right, then once we have them separated, right, this is a function of t. It happens to be constant with respect to t, but I can still integrate with respect to t. That's fine. I'll just pick up, this is a constant, we'll just pick up a linear term. So integrate both sides, and what do we get on the left? Y squared over 2 plus some constant. However, we talked a little bit about this. I'm going to collect the super constant, just one constant on the right that represents any combination of arbitrary constants that we might pick up. Okay, so y squared over 2 equals, and what's the right side? Right. Plus our constant. Okay. What is the overall question? What are we looking for? We know something about it.
the time at the original height,
So y, oh, and sorry. Y represents the height at time t. we are given an initial condition involving y. What was the original height?
12 feet.
And t, we should be careful, it's time in hours after noon, right? 12 p.m. Okay, so that's like time 0 represents 12 noon. And they tell us at noon, we get, what was it?
12 feet.
12 feet.
At 1 p.m. it's 6 feet.
Oh, and at 1 p.m., that's 1 hour later, it's 6 feet.
The question is how long until it feeds.
Yeah, and why do we need 2 pieces of information for this anyway? Any guesses? Why do they give us 2? Do we need to?
The
Can I-
rate of which the line comes out.
Right, I need a second data point. That's going to be able to tell me the rate of change of the height. So, yeah, if you look it over here, I do have 2. I got 2 unknowns we picked up. The original one, k, constant of proportionality, that talks about the rate of change of height. Okay, so let's use the condition here. I'm just going to call this condition 1. The initial condition 1 says that at time 0, the height is 12. Okay, so if I leave it in implicit form, that's fine, I think. But I know that when time is 0, the height is 12. Okay? So I can put 0 in for t, and on the right side, I'm just going to have that constant over here. But when I put in 12 for y, I'm going to get 12 squared 144 over 2, which is what? 72. Right? That zeroes out. 144 over 2, 72. Okay, so that gives us one of our constants. C is 72. I'm going to write it out front. Is that okay? C, and then I got minus k pi over t. Okay, and then what?
Now, put in the second condition that we had in 1, comma
Right,
6.
let's try that.
Or 6, comma 1. Or,
So we'll use the second condition, that after 1 hour we know the height to be 6. So let's take what we know here. We've solved for the first constant. We know that at time 1 the height is 6, so it cuts in half after the first hour. So when t is 1, the height is 6. So I'm going to have 6 squared, 36 over 2. I'm going to have 18, 72 minus k pi, k over pi. Sorry, 72. And then we can solve that for k. We'll have k over pi, move that over there, it's 72 minus 18, what's that? 54? Okay, multiply both sides by pi. 54 pi. Okay, so that's the other constant. So therefore we have this function. Now it is implicit, y squared over 2, but one thing we know is that the height will always be non-negative. So we could actually solve this for y. Should we do that, or do we leave it implicit?
solve it.
Okay, we can solve it. So negative kt, I'm going to write it like this, c, which was 72, minus k over pi. So 54 pi over, oh, and what happens here?
Pi crosses out with pi.
Right, okay. And t. So we get 70 minus 54t, well, it's linear. Well, that's y squared over 2, though.
72.
Why do I keep doing that? I want that to be 70.
Make it 70.
All right, so multiply both sides by 2, we get y squared equals back to 144 minus, what, 108t. And now you can argue that since, all right, if this were just a random equation, this would actually give an implicit curve, but it would be, there would be a top half and a bottom half. When I take the square root, y could be positive or negative. But you could argue that y represents the height of liquid in this thing measured from the bottom, so it's always non-negative. So when I take the square root, I only need to consider the top half. So what was the overall problem that we're trying to solve?
What time is it, does the tank physically
Right.
completely empty?
Right, so this is our height, y of t. We want the t value for which y of t equals 0. In other words, equals 0, right? And for a square root to be identically 0, the radicand has to be 0, right? That's the one-to-one function. The only time the square root function is 0 is when the argument is 0. So we got 108t must equal 144, right? And so t is 144 over 108. What does that give us? It's some times bigger than 1. What's that? 4/3. Oh, is that 4/3 right on the nose? So 1 1/3 hours.
1 hour and 20 minutes.
Okay, that makes sense.
Yeah, that's nice. And we don't have a repeating decimal. 1 hour 20 minutes. So interesting that the shape of this, in the first hour, it goes from 12 feet to 6 feet, but then it only takes another 20 minutes, another third of an hour to go from there to empty.
Well, it makes sense because it's the shape of it.
Yeah, most of the volume is going to be carried between 6 and 12 feet. That's going to have definitely most of the volume. Okay. All right. Well, that was fun.
Wow, right?
All right. Any other ones of lesser magnitude?
Can we do the offset question?
The what?
Offset question?
I don't do those in class. I'm willing to work on them with you if you come to me, because then we're working on them, and I know you've been working on it as opposed to someone just writing down the notes.
Why don't you write it?
After class, well, I got another class soon after that I got to prepare for. Tuesday and Thursday I got another class right after. Soon after this. Yeah.
Can you just re-explain the theorem 1.3, problem 13-14, the existence of a solution or uniqueness?
Right.
Real quick, go over that.
They give you, and this is a first course in differential equations, so I'm not going to be hardcore about knowing these and certainly not proving them. But in 1.3, when it talks about it in the section when you talk about direction fields. But theorem 1 in 1.3 talks about existence and uniqueness. So it's particularly a first order differential equation. What page is it? 24. So it's a first order differential equation of the form dy dx equals some expression involving both x and y, although if one of those was missing, then it's either integrable if it's a function of x only, or autonomous if it's a function of y only. But now it says if this function is continuous, and the way you'll determine if it's continuous or not is looking at it and finding out where the points of discontinuity are. There values in the denominator, for instance? You have x's or y's in the denominator that can make the denominator 0, and dy dx would be undefined. So it would be not continuous there. The function would not be continuous if its derivative does not exist. Okay? So if it says if this function is continuous and its partials, not necessarily both, but the partial with respect to y, and that's a strange, where does that come from? And its partial derivative with respect to y are continuous on some rectangle, that means some interval of x by some interval of y. And that rectangle contains the point A, B. So, this is the x-axis, the y-axis. Here's A, here's B. If the function is continuous on some band on the x-axis, including A, and some band on the y-axis, including B, and the point AB is in there, then there will be a solution to this. That's the existence part. Then it guarantees that there's a solution. The uniqueness part says there's only one solution. One and only one. So existence and uniqueness of a solution. And I'm not gonna have you prove that the function is continuous and its partial is continuous. That's gonna be by inspection, by looking at it. Where are those points of discontinuity? And basically, given this initial condition, if that's well away from any point of discontinuity, then there would be some interval on the x-axis that contains that, and it's continuous. And it says on some at least sub-interval containing that within the original interval, then there will be a unique solution to the differential equation. And this is all first order business. First order differential equation.
Can you give an example of one that's not and one that is?
I think there is a good, it has some remarks in the book after it where it talks about it. You might have a vertical tangent line, but off the top of my head, I couldn't come up with anything better than the book does. But yeah, so far I'm pretty happy with this book. I think the remarks after these theorems and examples are pretty good. Okay. All right, anything else? All right, let's see if I can actually do that a little bit. Okay.
Yeah. That's
All right, so today is what, the 8th? April 8th? Day 3. Okay, so last time we talked about, just a refresher, a certain class of first order differential equations, and those are separable. Okay, so these, example, something like dy dx equals 2xy. That would be an example of a separable equation that we saw last time. Through factoring, right, we can separate these variables to either side of the equal sign involving the correct differential. So, if we have this, 2xy, and we multiply both sides
I can't hear.
by 1 over y, yields the following. On the left, we'd have 1 over y times dy dx equals 2x. Now, what we have on the left side, okay, before I'm not even going to separate it, right, the dx on the right side. But what we have on the left side, if you look at it long enough, is a derivative of some function with respect to x. This is a derivative of some function y over x. So, in fact, that part of it, 1 over y dy dx, is the derivative with respect to the variable x of, well, derivative that gives you 1 over y, natural log y. Where y is a function of x. So notice that you have to use the chain rule and that pops out, but yeah, on the left side you got derivative with respect to x of natural log y with the chain rule. Okay? So this is not the way we always do it with separable. It's pretty easy. But this is an example. That 1 over y is an example of what's called an integrating factor. All right, so something that is multiplied to both sides of an equation so that the result is recognizable as a derivative. Recognized as the derivative of a function is called an integrating factor. Okay. Now, they often work on equations that are not separable, and that's what we're going to be talking about today, is another class of differential equations. Okay, and we will use integrating factors to come up with exact solutions to what's called linear differential equations, linear first order. Okay, and a linear first order differential equation is one of the form dy dx plus p of x times y, where p of x is just some function of x only, equals q of x. Okay, where the p and q of x are functions of x. Okay.
Just a quick question about the example you gave above.
Mhm.
So 1 over y would be the integrating factor on that one?
Yeah.
And why didn't you separate the dx to the other side?
right.
Typically.
Yeah, we typically would if it's separable. Now, equations like this don't need to be separable. So I'm using just an example of something that we would just do separation of variables. But you might note that multiplying both sides by 1 over y makes the left side the derivative with respect to x of some known function.
Sure.
Right? Natural log of y of x. Okay? So this is a different class. This is linear, and when they say linear, what they mean is linear in y, because I got dy dx plus something times y equals something. So there's no y's over here at all, but the coefficient functions, you can think of them, p of x and q of x. Okay? So those are like coefficient functions, but this equation is linear in y. And sometimes it's hard, you struggle why they call these classes of functions the way they do. So this is linear first order. First order, obviously, because it only involves dy dx. They write that as y prime plus p of x times y. Okay? So we will use an integrating factor . All right, and this is, they call it rho. Okay? So different than this function p of x, the coefficient function in front of y. But the integrating factor we introduce here is rho of x, and it's going to be e to the integral p of x dx. Okay? What I know. They go through an argument why this works, the theory. Okay? Read over it 2 or 3 times, but in the general, it's fairly, kind of tricky to understand. So they run you through it and they say, don't memorize this final answer at the end. Okay? That's the general solution. Okay, we're going to go through this and see why this works. And what we do with this is an integrating factor, so we then multiply both sides of the differential equation by that integrating factor. By the way, I'm going to call that equation 1 just so I can refer to it. Then we multiply both sides of 1 by that rho of x. Okay? So my note on this is, yeah, see page 48 for the general theory. I read it 2 or 3 times. But they even tell you, don't memorize. Don't memorize the final outcome, okay? But that integrating factor makes it differentiable, just like this does. It makes one side of the differential equation an integral, derivative of some function, okay? All right, some quick notes that might remind you. I'm going to keep these independent of these official notes. Some reminders that might be helpful. Certain integrals. So, for instance, integral with respect to x of e to the cosine x. Oops, not equals, but derivative of that. What do you get? Yeah, e to some function power. Notice it's always going to be e to some function power. But the derivative of this one, for instance, gives you, well, you always get that back, e to the cosine x, times the derivative of that, which is negative sine x. Yeah? Okay. What about this guy? Derivative with respect to x of integral of p of x. Oops, dx.
Does it just be p of x?
Oh yeah, derivative of the integral, antiderivative of p of x is just p of x. Plus c. Okay.
Wait, it's the derivative, wouldn't the constant go away?
Oh, you're, well, right. Well, yeah, and derivative, any constant would do here, because you're taking derivative. So any constant here would also make that, well, we can leave it on. All right, so we get p of x. Now finally, what if we do the derivative of e to the integral px dx?
P of x. You get p of x.
Oh, you just get e to the
P of x. P of x.
You get e to the
integral p of x.
E to the integral.
E to the integral of p of x times the derivative of that integral of p of x, which we just considered, right?
Oh, yeah, P of X.
So p of x pops out front, okay? And this is, yeah, this is what we're going to be handling with the integrating factor. It's going to be, oh, that's the derivative of something over here, okay? All right, so let's go through, let's do an example with the steps, see how it works. All right, and when we use that integrating factor, the result, I'm going to erase this part, you guys can see page 48, that's great. Okay, it's okay, don't worry about it, it's all right. The result on the left side of the original